barrier. No, that's a problem. You can't transport it.
Rip off your car and drag it to
Yeah.
yourself, take it.
Yeah.
Yeah.
Sounds like something my wife would do, like, get that out of the house. It's true. Makes a nice paperweight.
It's almost impossible to transport. That's the problem.
Yeah,
Yeah, you need a pickup truck.
Yeah.
yeah.
Ed used to do it with his son when his son lived around here, but he moved to Colorado.
I mean, Dobson used to take one around about that size and even a little bigger, to all the national parks.
Mhm.
I don't know what he carried it in.
Well, it's that, it's like the club I used to be in, chess club. It's like, if you didn't have a super big telescope, you weren't a member. That's just,
Anything less than 20, don't even join them.
that's right.
There's no point in giving it to a university of some kind, probably. Up a university, local, you know.
We don't know what to do with it. Very true. We don't know. I don't think they would want it, frankly. It's a beast. It's a beast. It's a really heavy duty scope. I don't know what we're going to do with it.
I think it's better if we have to move it.
Yeah. Yeah.
Section. You know, luckily I was in possession of it until someone wanted to borrow it. That never happened. I wound up taking it upstate New York, Pennsylvania, New Jersey, and we have Starport there. And up and down the 10-foot ladder all night long. Great views, but I couldn't walk the next day.
Dark is so sinking, that's.
Yeah.
Just like an orchard ladder
Yeah.
with, so, every 6 inches we had a step.
Yeah. Fire it up, Pete.
Okay, I'd like to welcome everybody to the March meeting of the Chesapeake County Astronomical Society. Like to remind people that we have an event going on tomorrow night at Great Valley High School.
Middle school.
Middle school, yes.
That's for elementary kids.
And yeah, it's gonna be elementary, it's gonna be like our last event where a bunch of little ones running around.
Yeah. 400 of them.
400. Well, yeah, last time was like 400.
Last week was 400 kids. I'm not sure what it'll be tomorrow. I have no idea.
And I'll turn the meeting over to Don here with his
Okay. Bruce, did you have something you want to announce?
side.
I just wanted to say, you know, I think everyone's aware, we started this Chester County Astronomical Society Scholarship for Westchester University students. And I'm really pleased to announce we raised about $3,200. And so as a result, we'll be issuing two $1,500 scholarships to two students that will be chosen probably end of April, early May by the committee. And we'll have some money left over in the account for next year. So I actually put the check in the mail to the foundation today. So I just really want to thank everybody. This is the first time we've done this. Really good turnout. I'm hoping it's something that the society does from now on, you know, to again solidify that bond with Westchester University. But thankful. So we're good. Excellent. Great.
All right. I have just one or two things to do. Hey, B, can you mute B?
Mute, yep.
Okay, I just want to show this has everyone been watching, let me get the lights. Jupiter and Venus, Jupiter is pretty much down now. That's about, I look pretty good.
That's good. That's great.
This is from like 2 weeks ago or so. Venus, and Jupiter and the moon, and just like a week ago or a week and a half, they were right next to each other. They're amazing. But the reason I want to show you this is from our house in Westchester. You can see it down here, you probably can't see. This is a little mark on here. It's called Nocturne. This was taken with an iPhone. And what you can do, I don't think they have Android available. Go to the next slide. But if you have an iPhone, you can download this. Stellar is one of the companies that make these automated telescopes. You put them down, you turn it on, and you stand back. it scans the sky, it aligns itself, and you tell it what you want to look at, and you get an image on your phone or your iPad or your tablet. You don't even look through the thing. It's amazing technology. I mean, they're a couple grand each, but they are amazing. But they have put out an app that is totally free. They use the same software. Like when I took that photo, it takes like 2 minutes, and it takes like 300 photos, and it aligns and stacks them on the fly. So if you have an iPhone, you need to mount it on something like this little tripod that I have the camera on, mount it on a little tripod, and it's amazing what it can do. So you can see, they got the color right. I mean, the moon is overexposed, sure, but it had to be to get classes. So if you want some fun with your phone and you need a tripod, I would say download. It's called Nocturne. Okay, it's really cool. Okay, so upcoming events. Pete was nice to mention tomorrow night we have a STEAM event. Last Thursday was STEM. Tomorrow night is STEAM. So science, technology, engineering, art, and math. Okay. We're going to be inside, and Roger and Kennedy will be there tomorrow night also with a solar telescope setup. And that's 5:30 to 7:30. And then our next Brandywine Red Clay events, they are this Friday. I don't know what the weather's like. I haven't checked it.
Good.
Really? But I'm going to be out of town, so we need somebody. If they're going to have it, we need somebody to open up. Then mid-April and mid-May. So those are the next coming events there. And the big thing coming up is Wolf's Hollow. That's at the end of April. For those of you there last fall with us, this is a great observing location. Now, yeah, it's at Wolf's Hollow, which is, where is it? Northwestern Chester County. It's about a half-hour, 40-minute drive.
Yeah,
Western Chester County, and it is an amazing place. So if you can help us out, this is the post at the Chester County Library. So we're doing this with the Act Glen Public Library. You can see, but registration required. There are no seats available. We limited to 50, and they sold out like they didn't charge. The registration filled up immediately. We bumped up to 60, and that's where we took to stop it. So these events are getting very popular.
You guys more than that in the fall, right? We had more than 60, I believe.
No, we limited that to 50, but I think maybe 55 came out.
Okay.
Yeah. So we said we'll bump it to 60. So but that's really a nice place for an event. So I'll just spend a few minutes. I see Scott is already on, so let me spend a few minutes on the night sky. Let's share stellarium here. So this is about an hour ahead. Let me just change my view here a little bit. I'll change that once I get done here. So Venus is still setting. Jupiter's already down. I had to set this an hour ahead because it's still light outside when I started this program up. There's still time to see some of the best things in the sky. And that would be the Orion Nebula. And you can see those with binoculars, any telescope. And I would say it's amazing. It is the most amazing nebula in the sky. Another really cool little thing is this coal car cluster, which is MGC 1981. And let's look at coal car. You can't really see it here, but you got wheels and a handle. It's a nice little open cluster. One of our favorite spots is up here along the belt of Orion. In a telescope, an eyepiece, this is really a beautiful S curve of stars between these two stars. You can get up to, I think, is it this one? One of these is the 37th cluster. I forget which one it is. It didn't really show up in here, but one of these looks like a 37 in the sky. Down lower, the little beehive, M41, a great little cluster. Right beneath the brightest star in the sky, Sirius. And yes, I'm serious. The little beehive is a great little cluster. There's all kinds of open clusters down here. You've got 46 and 47. These are both really nice little clusters. Higher up in the sky, we still have Auriga, and there's 3 right next to Mars. Okay, Mars is still nice to look at, but it is fading fast, falling behind. Still worth a look, but that's about all you get is an orange dot in the telescope. You can't see any features anymore. But these 3, starfish cluster at 38, pinwheel I think is 36. My favorite is 37. And the reason is it's the most complex and most filled with stars of those 3 clusters up there. So, but they're nice compared to 3. And if you have binoculars, the single best sight in the sky, I think, well, other than perhaps the Pleiades, the Beehive cluster is probably the next best thing in binoculars, because, and you need binoculars. It won't fit in an eyepiece of a telescope. It's huge, absolutely huge. If you get a really dark night and a good spot, the Leo triplet is certainly going to be on your list. And probably you should have 8-inch to catch these 3. I can almost always catch these 2. This Hamburger galaxy is the faintest and it's a little hard to get, but you can get them. Historically, a real interesting star is this one. This is Algeba. And this star is a double star. It doesn't show up here. There, you go really in, you can see a double, but this was observed by William Herschel. And he observed it over years. And it was the first time that it was understood that gravity works out in space just like it does in the Earth. They could tell that these 2 stars were orbiting each other and attracted by the gravity to each other. So it really was historically a very significant star. I guess that's all I need to cover now. Any questions from anyone, Zoom or live? If not, Bruce, you can introduce Scott.
Sure, great. So to everyone coming tonight, it's a pleasure trying to introduce you, Dr. Scott Dowdy from Ohio State University. I think it's fair to say he's a pretty renowned exoplanetologist, if that's a real word. Dr. Dowdy is the Thomas Jefferson Professor for Discovery and Space Exploration in the Department of Astronomy at Ohio State. He's been a faculty member there for about the last 17 years. And he basically is a leader in the discovery and sort of the statistical characterization of extrasolar planets, and uses a variety of different methods, some of which I'll discuss tonight in this talk, not just the more familiar transit methods, but also gravitational microlensing. In 2008, he and some of his collaborators announced the discovery of the first Jupiter-Saturn analog. And through the course of his career, he has been involved basically in using a lot of different analytical and numerical techniques for assessing sort of the utility of both current and next generation survey methods for evaluating and characterizing exoplanets. He's a member of the science definition team for NASA's Wide Field Infrared Survey Telescope, and he's the chairperson-elect for NASA's Exoplanet Exploration Analysis Group. He's received numerous awards in the course of his career from the National Science Foundation, from the Astronomical Union, and I think one of the most prestigious ones was about 6 years ago. He was awarded the NASA Outstanding Public Leadership Medal in recognition of, quote, his outstanding leadership as the Exoplanet Program Analysis Group chairperson, having significant impact on NASA's search for exoplanets and life in the universe. And to his credit, I believe right now he is credited with the discovery and characterization of over 100 exoplanets. So it's really a privilege to welcome Dr. John. He's listening to this guide on completing the census of exoplanets in the galaxy using the Nancy Grace Space Telescope. Scott, thank you.
Okay, can everyone hear me?
Yes.
Yep, really well.
Thanks for the introduction. Glad to be with you virtually. I'm going to be talking indeed about completing the census of exoplanets using the Nancy Grace Roman Space Telescope. Or I could alternatively have titled this talk, How to Find All the Exoplanets. So I'll just jump right in. So I like to start my talk with this figure. This is an artist's conception of what our solar system looks like. The sizes of the planets here are to scale, but the distances from the sun are not. And I've done a little revisionist history here and removed Pluto. But these are the 8 planets in our solar system. And if you had to construct your own solar system from scratch, you might not come up with something like this. So we have 4 big glorified balls of rock, one of which we're currently standing on, that live in the inner part of the planetary system. There's an asteroid belt, and then as you go further out, the biggest planet in the solar system, the most massive and largest planet, Jupiter, is sitting right smack dab in the middle. And then as you go further out, the planets more or less decrease monotonically in mass and size, and become ever further away from the sun. So this unusual architecture of the solar system needs explaining. And we had several hundred years of thinking about why our planetary system looked like this. And we, not surprisingly, came up with a very compelling theory that exactly predicted what we saw. It's very easy to come up with a theory to predict one data point. That theory turned out to be, if not wrong, at least substantially incorrect, and that's part of the story here. But it took us a long time to actually be able to detect planets around other stars. It wasn't until the 1980s that we really developed the technology that we need to detect planets around other stars. And one of the main technologies that we developed was the CCD camera, much like what you have in your cell phone. And that enabled us to bring astronomy to the digital age and allowed us to increase our sensitivity of our instruments. So the reason why detecting planets was hard is because they're quite small. So this is kind of a strange thing to think about, given that we're standing on a planet that is so vast that it appears flat, even though we know it's spherical. But the Earth is, in fact, is actually quite small, especially compared to the sun. So if we just look at the sort of metrics of how we measure the scale of planets, Jupiter is about 10 times smaller than the sun. It's about 1,000 times less massive than the sun, and it's about 250 million times less luminous than the sun. For the Earth, it's the numbers are even more astronomical. The Earth is 100 times smaller than the sun, about 330,000 times less massive, and about 1 billion times fainter. So those are all very small numbers, and because we want to detect the planet next to its parent star, we have to fight with these large numbers. But as I said, we developed the technologies and the techniques that allowed us to do this in the late 80s, and the first detections came not long after in the early 90s. So the methods we have at our disposal, some of which you may be familiar with. So we have the Doppler method. This is kind of the first method to detect, not really the first method to detect exoplanets, but the first one to detect exoplanets in bulk. Here you're taking advantage of the fact that planets don't orbit the star; they orbit to the center of mass of the planet-star system, and therefore, as the planet orbits around the star is orbiting around the center of mass itself and wobbling on the sky and along our line of sight. So, by measuring the Doppler shift, same way you measure radar, they measure your speed with radar. You can determine if the star is moving towards you and away from you, and if it's doing so in a periodic manner, then you can infer that there's a dark body orbiting it, and you can infer its mass and its separation and its period. And so some of the first planets were discovered by the Doppler method. The astrometric method is similar to the Doppler method, except now instead of looking for the motion of the star along your line of sight, you're looking for it on the plane of the sky. And here we only have a handful of detections, but there's many more that are coming. Probably most people are familiar with the transit technique. Here you're just using the simple fact that you can't see through planets. So if you have a planet orientation that happens to be along your line of sight, that planet will pass in front of its star once per orbit, cast a shadow on that star, block some of the light from the star, and the star will become dimmer by some amount, depending on the size of the planet relative to the star, for a brief period of time. And so you monitor the brightnesses of a bunch of stars, see which ones go dip, and then from there you can infer the existence of planets orbiting those stars. Direct imaging is in some sense the simplest method to understand. You're basically just looking for light from the planet separated from the light from the star. And this is one of the most famous planetary systems discovered by direct imaging, HR 8799. You can see the 4 planets there orbiting about the central star. The central star here has been blocked out, which is why it's black. But the planets, you can see the 4 planets orbiting it over the course of sort of over 10 years. And the method that I spent a lot of my career developing and using is the microlensing method, which I'll talk about more later. And there's other methods to detect planets, but I would say these could be fairly characterized as being more niche and not really able to survey the broad kinds of planets that we think might be out there. So the game really changed in 1995. This happened actually a few months after I started graduate school at Ohio State. The planetary companion to 51 Peg was discovered, 51 Peg B. This is not actually the first exoplanet discovered, although that's a common misconception, but it was the one that really jump-started the field. And although we had a theory that predicted our solar system, which predicted that giant planets like Jupiter and Saturn should exist in the outer parts of their planetary system, 51 Peg B is a Jupiter-sized, roughly planet orbiting a very normal sun-like star, except its period around its star is only 5 days. So well interior to the orbit of where Mercury would be if it orbited this star. This came as a huge surprise, so much so that some people doubted the existence of this planet at all. But we've since confirmed these kinds of planets do exist and are still looking for explanations for how they get to where they are. We don't think they form there, but we think they migrate there like retirees moving to Florida. Okay, so in the intervening however many years, we've discovered now over 5,000 exoplanets using a wide variety of techniques with a wide variety of properties. So this plot shows on the left here the mass of the planet as a function of its period, and then on the right the radius of the planet as a function of period. And so these are all the known exoplanets as of a couple months ago, and they're color coded by the method that is used to find the planets. And then our solar system planets are shown here. And so you can see this unusual architecture in our solar system imprinted on our solar system on these diagrams, where you have these sort of glorified balls of rock here, and then you have these giant planets out here. And so what you see is that there's lots of planets, and we can now start to ask, where do planets live in the plane of the mass and period or mass and semi-major axis? We can start actually taking a census of exoplanets in the same way we take a census of people in the United States, and just ask, what are they like? Where do they live? What are their properties? And that helps us to try to refine our theories of planet formation, which we now know, based on the discovery of 51 Peg and many other planets, is woefully incomplete. And these planets are really quite varied and in their properties. So these are really strange new worlds. So one planet that I had the privilege of helping to discover is Kelt 9b. This is a planet that is roughly twice the mass of Jupiter, orbiting a star that's quite a bit hotter than the sun. It's a blue A-type star, like Rigel, not Rigel. I'm blanking now. Sorry, Sirius, like Sirius or Vega, A-type star. And this planet is orbiting only a few days from its with a period of only a few days, very close to its parent star. And it is the parent star is so hot and it's so close to its parent star that the dayside temperature of this planet is actually hotter than most stars. And the planet itself is actually evaporating with time. And so this is an artist's conception of this planet orbiting over the pole of the star, and you can see it's leaving this trail of hydrogen as it's being evaporated and blasted by its parent star. We have planets that are water worlds. We think they're covered with thick oceans and no discernible land. We have planets that are lava worlds. They're rocky planets so close to their parent star that the rocks are actually in semi-liquid form. Kelt 1b is another planet I helped discover. This is a planet, well, sort of a planet. It's a heavyweight planet. It has a mass of almost 30 times the mass of Jupiter, but it has a period of only about 29 hours around its parent star. So this is either a giant planet or a failed star. We don't really know. We have planets that are in between the mass of the Earth and the mass of Neptune, for which we have no analogs in our solar system. I'll talk a little bit more about these super Earths or mini Neptunes. We have planets in multi-planet systems. One of the most famous is TRAPPIST-1, which is 7 planets, of which 4 of them are in the Goldilocks or terrestrial or habitable zone of their parent star. But they orbit a star that's much less massive than the sun. The size of the star is actually roughly the size of Jupiter, and the mass is roughly 1/10 the mass of the sun. This is going to be a great target for JWST, which I'll talk about later. We have cold planets, or planets that are located far from their parent star but are still hot from their formation, like 51 Eridani b. We have planets orbiting dead stars. So a planet discovered by the microlensing method is orbiting a star, the cinder of a star, a white dwarf, after it dies. It's a Jupiter mass planet located, at roughly Jupiter separations from its white dwarf star. And then we have planets that are orbiting 2 stars, just like Tatooine in Star Wars. So really, these are strange new worlds. And I think the lesson we learned from this is that Mother Nature is far more imaginative than we are. Basically, every kind of place you look for a planet, you find one, and every rock you overturn, you find a planet. And there seems to be no end to the diversity of the kinds of planets we see. So finding individual planets is interesting, and studying them is interesting, but really performing the census is one of the main ways we're going to really understand how planets form and evolve, and ultimately ask questions like, is our solar system common, unique? Why does our solar system look the way it does? Does that have anything to do with the fact that there's life on the third rock from the sun? So the first mission and survey to bring exoplanets into the statistical age is the Kepler Space Telescope. This telescope was about 1 meter in diameter, a little bit smaller than that, and it relied on the transit method to find planets. So it stared at roughly 100 million stars for just under 4 years, looking for these periodic dips as the planets passed in front. And it had very exquisite ability to measure the brightness of the stars, so it could find very, very small dips, like the size of Earth passing in front of the sun, which only dims the star by 1 part in 10,000 for about 10 hours out of 1 year. But this mission was designed to detect those dips. And so again, using the transit method as I just described. And it found many planets. It found planets of all shapes and sizes, located at many different separations from their parent star, around stars of many different sizes and masses. So this is just a subset of the planet, an artist's conception of the subset of the planets, where the size of the star is proportional to the true size of the host. The shadow is proportional to the true shadow size. In some cases, you can see multiple planets there. So you can see these kind of Jupiter-sized planets orbiting giant stars. This is what Jupiter and Sun would look like in this diagram. And you find bigger planets orbiting smaller stars, and even smaller planets orbiting smaller stars. So vast array of planets. And one of the first results from the Kepler Space Telescope that came out was that the most common kind of planet that Kepler found has no analog in our solar system. These are these super Earths, or mini Neptunes, with radii between that of the Earth and about that of Neptune, about 4 times the size of the Earth, and masses between roughly the mass of the Earth and something like 20 times the mass of the Earth. These planets are exceedingly common. They're found at very small, relatively small orbital separations with periods of less than 100 days around most stars in the galaxy. And so this, again, was quite a surprise because we have no such planets in our solar system. So these are the planets in mass that Kepler found a bunch of, and they're in radius. And you can see there's this large number of thousands of planets detected by Kepler. So Kepler really, kind of filled in, did the first part of the census. It filled in the parameter space here and told us where planets were living, at least planets with relatively short period orbits. But what about the planets out here where our solar system planets live? Well, you can see there's not that many detections. And that actually turns out to be because of the techniques that we've developed to detect planets are not sensitive to planets out there. So at the moment, we've only barely really surveyed the entire parameter space of planetary systems. We don't really know how common solar systems like ours are. And we really need to develop new techniques to detect planets in this region. So we really want to do is complete the census, again, to understand how planets form and how common solar systems like ours are. Okay, so back to our methods of detecting planets. What should we do to pick this one? Well, it turns out the method that is most sensitive to planets out in the outer parts of its planetary systems, at least relatively low mass planets, is gravitational microlensing. So this is a technique that was was actually the way it basically works is that if you stare at a star in the sky long enough, then eventually another star will pass in front of your line of sight to that more distant star. That foreground star will split the light from that background star into two images. Those images are too small to too closely separated in the sky to be resolved, but they change in brightness in a very predictable way. And so you can see this background star get brighter and fainter as the foreground star passes in front. And if that foreground star happens to have a planet, the gravity of that planet can act like a lens, just like its host star did. And oops, you can get, so you can see here, the background star is getting brighter, and the two images of the background star are getting brighter, brighter. Now they're brightest, now they start getting fainter, but now the planet passes in along the line of sight, and that image gets brighter temporarily. So what this looks like is a smooth curve in brightness where the star gets brighter and fainter with a little bit of bump on top of it due to the planet. And so those little bumps are the signatures of planets orbiting these foreground stars, and you're very sensitive to very low mass planets using this technique. This phenomena was originally, the phenomena of microlensing itself was originally proposed by Einstein, although he famously predicted it would never be observed. He was quite wrong about that. We've now detected tens of thousands of microlensing events. And his use as a planet discovery method was first proposed in the early 90s, including by my former advisor, Andy Gould at Ohio State University. And when I started in 1995 as a graduate student, I started working with him, and he and I kind of worked together to develop this method into a theoretical idea of how you could find planets to an actual viable method of detecting planets. And the first planet detected by microlensing was discovered in 2003. And this just to show that I'm not making all this up. This really does happen. This is a background, a somewhat smooth background image of a set of stars in the galactic center of our galaxy. And you get, fortunately, nature has circled the star we're interested in this case, so we know to look at it. And you can see that the background star gets brighter and then fainter, but then as the planet passes close to the line of sight, you get this extra little blip. And again, nature's nice, it turns the circle red, so you know when to look. That's the signature of the planet. So this was the first planet discovered by gravitational microlensing, and we've now discovered over 100 planets using this method. Okay, so where do we go from there? Oh, and the thing about this method that makes it exciting is that these images that you see here, they're passing quite far away from the host star, the foreground lens star, at separations roughly where Jupiter and Saturn are from the sun. And so that means that planets in that region of the planetary system are the ones that are going to create these little bumps. And so we can detect these long period planets and very low mass long period planets by looking for these bumps. And it's very complementary to the other methods we have at our disposal in that it's sensitive to basically a complementary region of parameter space. And so together, by combining this technique with something like Kepler, we can complete the census of exoplanets. And that's the goal. So where do we go from here? Well, it turns out that gravitational microlensing is an extremely rare phenomenon. So I said, if you look at a star long enough, you'll see another star, foreground star, pass in front. Long enough here turns out to be hundreds of thousands of years, so much longer than a graduate student lifetime. So instead of looking at 100,000 stars, we look at one star for 100,000 years. We look at tens of millions of stars or hundreds of millions of stars for a couple years, and at any given time, hundreds of those stars are being lensed. But that means that we have to look at a lot of stars and measure their brightness continuously because we don't know when these things are going to happen. And that requires a very large field of view. And so as we were developing this method during my graduate school career and afterwards, and me and the rest of the people working on microlensing in the world, we sought to use ever larger detectors to image more stars and get more microlensing events. But ultimately, we're limited by the fact that if we want to really monitor a lot of stars, we have to do it at very high angular resolution, and we have to be able to do it continuously, and we don't want to have to worry about when the sun comes up. And so this meant that there was a natural limitation for doing this on the ground. So that's where the Nancy Grace Roman Space Telescope comes in. So I have to take a little detour here and talk a little bit about astropolitics, which is something that I've come to become involved with sort of accidentally. Sometimes call myself an accidental astropolitician. So how does astronomy missions, how do they get prioritized and built and launched, right? It's not, you might think that, oh, it's a bunch of really smart old guys sitting in their ivory towers in Harvard and Princeton that decide, yes, we should go and do this mission. And then, NASA then goes and builds the mission. Well, that's not how it works at all. How it really works is that the astronomical community every 10 years gets together. They elect their sort of 20 most, the smartest people in the field that do a bunch of different kinds of astronomy. And those people get together, they solicit information from the astronomical community as to what people think astronomy should be in the next 10 years and what should the US government be spending their astronomical budget on in the next 10 years. They take this information, they collate it, they prioritize it, and they come up with a list of recommendations. And that list of recommendations is taken very seriously by NASA and NSF. In fact, they're congressionally mandated to pay attention to this. So this activity is carried out by the National Academy of Sciences, and it's been happening since 1970. So every 10 years, these decadal surveys happen, and we prioritize what we want to do for the next 10 or more years. So in 1972, the first decadal survey happened, and one of the biggest priorities there was the Hubble Space Telescope, which eventually came to be. Next decade, 1982, was the Chandra Space Telescope. This is an X-ray telescope, also came to be. After that was the Spitzer Space Telescope. This was an infrared telescope, which was launched and actually now is already done with its mission. And then I think everyone's here has probably heard of the James Webb Space Telescope, or Webb, JWST, which was prioritized by the 2000 decadal survey. And it took, over 20 years to build this thing, but it has now since been launched. So just quick reminder, JWST is about 6.5 meters in diameter. It is a foldable mirror, so it could fit in the rocket. It's coated with gold. It's made out of beryllium. It has this large sun shield that you see here. It's quite a massive undertaking and very complex. But it was built, it launched, it worked, and is now doing lots of great astronomy, as you all know, including searching for planets and characterizing planets. But JWST's field of view is actually quite small. It can't actually look at very many stars at any given time, right? It doesn't have, let's say colloquially, it doesn't have a wide angle camera lens, which is what you want for gravitational microlensing. Well, that brings us to the next decade, in 2010, when the decadal survey prioritized a mission called the Wide Field Infrared Survey Telescope, or WFIRST. So this was about 10 years after I got my PhD. I had been working on gravitational microlensing for 15 years. I've been advocating for a space mission that would enable us to go and look for microlensing events, and the decadal survey, lo and behold, advocated for a mission that, among other things, would actually survey hundreds of millions of stars to look for microlensing events and complete the census of planets begun by Kepler. So since then, in the last 13 years, I've been working on the WFIRST, which has since become the Nancy Grace Roman Space Telescope, helping to develop it from a mission, this just kind of nugget of a mission idea, to an actual mission that is currently being built. So this is an artist's conception of what the space telescope is going to look like. It is not very big in the scale of things. It is roughly the size of the Hubble Space Telescope in terms of its mirror size. So who is Nancy Grace Roman? Well, if you're not familiar with her NASA history, Nancy Grace Roman was the first chief astronomer of NASA. She's often called the mother of Hubble because she was instrumental in getting Hubble off the ground. So she's really an icon, and when they changed the name from WFIRST to Roman, we were all quite honored to be able to take on her name. So, like I said, it's not a huge telescope. It's smaller than JWST. It's actually just not any bigger than the Hubble Space Telescope. It's about a 2.4 meter mirror. And it looks at wavelengths that are very Hubble-like, the even narrower range of wavelengths than JWST. So wavelengths that our eyes can see, and then slightly longer. It isn't even able to look at shorter wavelengths, which Hubble can look at, the ultraviolet. It has two instruments, as opposed to JWST or HST, which has more instruments. One of them is a coronagraph that's designed to do direct imaging. It's a subject for another talk. But the other is this wide field camera. And this is the key to what makes Roman so powerful. because Roman, even though it has the aperture of a Hubble, it has 100 times the field of view. So this shows the largest field of view of Hubble or JWST, and this in the white squares shows the field of view of Roman. So it is 100 times larger than that of Hubble. You can look at 100 times more area in the sky at any given time, but with the same sensitivity and same resolution as Hubble. So that means it can map large areas of the sky quickly or smaller areas of the sky, but repeatedly over and over again. And that latter is the exact capability we need to do microlensing. Because again, though microlensing is sensitive to planets at the separations that we need to start surveying, it's very rare phenomena. So we have to look at lots of events to detect planets. So the way it's going to work, the way it was envisioned by the decadal survey is going to work is that Roman will stare at the center of our galaxy where there's lots of stars to look at. And these stars, are just flashlights for us. We don't really care about their properties that much. So we'll look at the very center of our galaxy, which actually has a lot of dust along the line of sight, which is why we want to look in the infrared. And we'll monitor about 7 fields, some of those fields I just showed you, just cycling through them repeatedly every 15 minutes. And we'll get images that look something like this. So this is a simulated image of what Roman will see. You can see stars of various brightnesses and various colors. You can see these little rings around the star. Those are diffraction rings, and that tells you have very good angular resolution, all the things we need for microlensing. This is not very many stars, but fortunately, this is nowhere close to the field of view. So zooming in on that, that's the field of view. That's the field of view I just showed you. That is a larger field of view, still well within the area of the Roman's wide field instrument. That's 0.1% of the survey area. That's that initial thing I just showed you. That's 0.0005% of the survey area. So if you take this larger image in the back and multiply it by 1,000, right? Imagine how big that would be. Those are the stars that Roman will be monitoring towards the galactic bulge continuously every 15 minutes. There's hundreds of millions of such stars, and so they'll be sensitive to, we'll be able to detect tens of thousands of microlensing events and detect thousands of planets. So we've done simulations to show what Roman might be able to do. So we inject microlensing events into our fake images, and then we measure the flux of those microlensing events as a function of time. We inject planets into them. So this is the microlensing event due to the star. We inject planets into them. We see planetary perturbations, and then we ask, can we detect those planetary perturbations? And you can see here the fact that this is the noise here showing the scatter and the points. This is the signal. Signal to noise is very high. It means we have a very robust detection of a planet. All right. So this particular system is that planet has a mass of twice the mass of the moon, but it's located at a separation of the same separation between Jupiter and the sun, 5.2 astronomical units. It's a very robust detection, as I mentioned, and so we have sensitivity to planets with mass all the way down to a few times the mass of the moon, which is pretty impressive. We've never only detected a couple such exoplanets using other techniques. Because planets have gravity, they can act as lenses even if they aren't orbiting a star. Their gravity can bend and magnify that background light in the same way the star can. And so we're sensitive to planets without host stars or free-floating planets, quite sensitive to them with Roman. So this just is 4 simulated detections with Roman kind of data of free-floating planets. One at the top left is a free-floating brown dwarf or failed star with mass of roughly 60 times the mass of Jupiter. The one below it is roughly a Jupiter mass planet that you can see, again, very clear signal. The one in the bottom right is a free-floating Earth mass planet. This happens to be lensing a very large star, which is why you get this flat top shape. And then the very top right is probably the most impressive. This is a Mars mass planet that is creating a microlensing event. So it's a free-floating Mars mass planets. And just like we have predictions for where planets bound to parent stars should live, we have predictions for how common free-floating planets should be. And we generally think planet formation is a very messy and chaotic process, and so lots of planets get kicked out in the process of forming planets. So we expect a lot of free-floating planets, and Roman will find them. Like I said, we're sensitive to things all the way down to the 2 times the mass of the moon. So that means we're sensitive to moon mass things orbiting giant planets as well. So we're sensitive to moons like Ganymede, orbiting Jupiter. And so I've been working with an undergraduate at Ohio State, Matthew Listowska, and his senior thesis was to simulate moon signals with Roman. And you can see here, this is an example of a Jupiter mass planet located at about 8 times the distance of Earth from the sun, or about the distance of Saturn from the sun, a little less. And it has a Mars mass moon that's creating this extra little bump that you see right here. So a very distinctive signature of a moon. So we can in principle probe the frequency of extrasolar moons. We can also probe the frequency of planets orbiting binary stars, solar system analogs, many different kinds of planets using this technique. But the sheer power the real power of this technique is where it is sensitive to what kinds of planets. So if I showed you a plan view of our solar system, which I've now put Pluto back in because it suits my purposes for this case, you see the orbits of the terrestrial planets are located within this little white circle here, then Jupiter, Saturn, Uranus, Neptune, Pluto. That little red dot, that is the region of sensitivity of the Kepler Space Telescope. Just that very inner part, right? The rest of the planetary systems, that Kepler monitored would not be sensitive to planets out there. And that's why we don't know how many planets are out there. So this just shows a blow up of that. Again, thousands of planets were discovered. Kepler was not a failure, but it did not probe this outer region of planetary systems. This is the region that would be probed by Roman. And so you can see that it really probes the entire planetary system, at least analogs to our own planetary system. And together they probe everything. And that's the real power of combining these two techniques. So this is how we find all of the planets. That's Roman search area. Another way to show this is to show it in a plot like I showed before. So on the y-axis, we have planet mass and Earth masses. On the x-axis, the separation of the planet from its star in astronomical units. So that's 1 AU is the separation of Earth from the sun. You can see little cartoons of the solar system planets here. These are the planets detected by Kepler in red. This red line shows where planet Kepler was sensitive. So interior, shorter periods and larger planets, Kepler was sensitive to those, but not out here. And this is the region of sensitivity of Roman, right? So it's sensitive to analogs of all the giant planets, or all the planets in our solar system, except for Mercury, and even sensitive to some massive moons out here. And it's also sensitive to free-floating planets. And in particular, another thing I'm actually quite excited about is it's sensitive to analogs to our ice giants, Neptune and Uranus, at the separations of our ice giants. And there's no other technique that we know of that can do that. So together, by combining Kepler and Roman, we can really find all the planets and do a census of all the planets and figure out where they live, what their properties are. And so ultimately place our solar system into context and try to understand how planets form. So, so Roman was prioritized, 13 years ago. Where are we now with this process? Well, we're actually quite far along. And this is what I want to leave you with, right? This is not some pie in the sky future mission that's not going to happen for another 20 years. This thing's going to happen soon. It's happening, right? So I talked to you about this field of view. So this field of view is enabled by 18 detectors. You can count each one of them here that are arranged in this smiley face or frowny face if it's upside down. Each of these detectors have 4,000 by 4,000 pixels. The whole camera is about 300 million pixels. And here are the detectors for this. We have the detectors in hand. They've been built, they've been manufactured, they've been put in the detector array. So we have a 30 megapixel camera, 300 megapixel camera that is ready to go and after launch. This shows images of, so each row here is a different detector, each column is a different detector, each row is a different property of the detector. So we've characterized the detectors, they all have personalities, but they all pass our specifications that will enable us to do the science that we want to do with Roman. We have a mirror. It's been polished, it's been coated with aluminum, and it's ready to go. We have, this shows another view of it, just so you can get a sense of the scale. This shows the mirror now incorporated into the thing that's going to hold it. This shows that structure itself being put on struts. You have the six actuator system, so you can point the mirror correctly. And this just shows the whole system now bundled up into the spacecraft. This shows the secondary part of the system. So this thing is going to go on top of that, what I just showed you. You can see the secondary mirror here. So the light comes in here, bounces off the primary to the secondary, bounces through the hole in the middle of the primary, and then gets turned into focused on the detector, turned into electrons and this data. This shows another version of it to scale. And so these things are all now assembled together. We have our filter wheel. So it has several different filters that you can see here. Each one of these circles is a filter. Filters are about maybe this big. They're arranged in this wheel. So you turn the wheel and you can look at different wavelengths of light. And this just shows to scale roughly what that filter wheel looks like. One of the things about the Roman Space Telescope that makes it unique is the very large volume of data that we're going to get. So the data rate is extremely high. To get that data down to Earth from its orbit at the second Lagrange point, which is where JWST is, we need a very high gain antenna. This shows the high gain antenna being tested at Goddard Space Flight Center. So the point is that we are building now, we're soldering things together. This mission is going to happen soon. So if we look at the timeline of this mission, this shows year to 22, 23, 24. This is where we are now, here in middle, a little bit, third of the way through 2023. This is we're in what's called phase C of the project. This is where you're building the components. Phase D is where you integrate them all into one thing and then test that big spacecraft in a variety of methods. And then here is launch in late 2026. And right now, in 1 week, proposals are due from scientists in the US to help to develop the software pipelines, the data reduction pipelines, the analysis tools to take advantage of all this data and turn that data into science. And I am leading a team of about 50 people. So I'm taking a little break from writing this proposal to share this with you today. About 50 people to propose to build the machinery we need to extract the science from this mission. Just to show I'm not making this up, this is our timeline and our plans. I'll go through all of this, but each little triangle is something we have to do and when we're going to do it. And I just want to focus on this particular thing. This is launch October 2026, and it is less than 4 years away. And so this is happening very soon. So stay tuned. The launch date might slip a little bit, but probably not a lot. We've been sticking to schedule and we're on time. And so within 4 years, you should start seeing lots of pretty pictures of the center of our galaxy. We'll see how close our simulations are to those. You'll see lots of microlensing events. You'll see some planetary detections. And then you'll know that we're finding all the planets. So I'll leave it at that. Thank you.
Questions.
So Scott, can
Yeah.
you hear me?
Yep.
Your modeling was looking at individual planets around stars. If other star systems have solar systems like ours with multiple planets, how will you deconvolute that image from a single star that you were modeling as a single planet around a star? It may be much more complicated than that.
Yeah, that's a great question. So indeed, when you have multi-planet systems, which we hope will detect multi-planet systems, we do expect to detect multi-planet system. The modeling does indeed become more complicated, but it's something that that we've been thinking about now for like 20 years, and so we really have a pretty good idea of how to do this. But there's still work to be done. In fact, I'm working with a graduate student at Ohio State right now, just started, whose project is to try to simulate some of these events and see how challenging they are to actually analyze. But it's a great question.
Have you been at the vehicle spacecraft assembly facility? Have you seen?
I've been to Goddard, where they're currently where they're going to assemble it. Right now, part of it is in Ball Aerospace and other parts of it. So they haven't quite gotten to the point where they're putting everything together at once. But the pictures I showed you, a lot of those were in Ball Aerospace. I haven't been there yet, but I've been to Goddard, and that's actually where JWST was, part of JWST was assembled. And that image I showed you was the JWST turning around was from Goddard Space Flight Center.
Looking forward to seeing it.
Scott, maybe somewhat of a naive question. I'm just curious. Would any of the techniques, especially gravitational microlensing, be able to detect planetary systems where you may have subsurface oceans? So not a surface ocean, but like a Europa or a Callisto type planet. Or would the technique simply not be able to make those kind of measurements? I'm just thinking in terms of wobble and shift. Would it be difficult to infer?
Yeah, so I mean, we could definitely detect planets that have subsurface oceans. Could we detect that they have subsurface oceans? That's tough, because basically there's almost no exchange from this exchange of information from the subsurface ocean to the atmosphere of the planet or the outside of the planet, which is what's directly observable through photons. You can ask one way to pose this question is how do we know that Europa has a subsurface ocean? Well, it was actually predicted by theory, but the way we know is because it induces Jupiter's magnetic field induces a magnetic field onto Europa's ocean, onto Europa through its ocean. So if we could, in principle, detect magnetic fields of individual moons around giant planets, we might be able to do this, but that's pretty science fiction-y compared to our current capabilities.
Kind of an unrelated follow-up, but just if you would speculate. You mentioned in the beginning that a lot of our theories of our formation of our own solar system were pretty off. And I'm just wondering, is there any speculation why we don't have super Earth type planets in our system?
Yeah, there are models. Yeah. So one particular one that I find compelling is that our planetary system. So planetary systems form protoplanetary disks, so you have a disk of gas and dust, and it kind of collapses to a flattened system. Dust kind of condenses out of it, starts sticking together, and forms ever bigger planets. And then at the end of the day, the gas goes away, and you're just left with planets. That's the idea. If that process was slow enough, then you didn't form very many planets and you didn't form very big planets. So you ended up with this kind of dichotomy of small, basically leftover debris of planets like the one we live on, and then just one or two giant planets. That's one theory, but there's lots of different theories for how this works. But it probably comes down to the initial conditions of the system, which is how massive the disk was, for example. So we may have lived in an undermassive protoplanetary disk compared to other solar systems, planetary systems.
Got the first one discovered, the PEG 51, is that right?
51 PEG. It's not actually the first exoplanet discovered, although it's often thought.
That's a Jupiter-sized rotating, orbiting very close to the star, right?
Roughly 5 days, I think. Yeah.
Right. Now, haven't I heard that in our solar system early on, Jupiter was very close, much closer to the sun than it is now?
We don't think so. No, we think Jupiter formed fairly close to where it lives right now. It may have, there's a model called the Grand Tech model where it migrated in closer to like where the asteroid belt is and then migrated back out. But it certainly never got close enough to be what we call a hot Jupiter. Hot Jupiters almost certainly didn't form there. It's very hard to form a hot Jupiter where they currently live. There's other physical processes that we've since come up with that explain how you migrate these hot Jupiters from their cold outer birth sites to their very warm current orbits.
Right. So what you're seeing there, 51 PEG, is very unique.
So it turns out about 1% of all solar-like stars have what these called are hot Jupiters. So they're not super common, but they're not super rare either. And why 1%? That's another open question that we haven't yet solved. The reason why we found that one first, of course, is because it's basically the easiest planet to find. That's why.
Just got another question. The JWST showed that L2 is probably not as clean as we thought with regards to micrometeorites. What does that mean for future?
Yeah, so people that are not familiar, there's micrometeorites, and they budgeted for these. So JWST is, as you saw in that picture, is just a mirror sitting off in space. There's a sun shield on the bottom that blocks the sunlight so it stays cold, but micrometeorites can just come right and hit the mirror, and they do. And what happened was one was big enough and had enough momentum that it hit the mirror and knocked it out of alignment. They were able to put it back, but they expected that thing to happen, that kind of event to happen once every 5 years, and it happened within the first few months. Could have been that they're super unlucky. They don't know. They're not super worried about it, but they're a little worried about it, enough so that the next mission after Roman, which is called the Habitable Worlds Observatory, which is a topic for another talk, was originally planned to be one of these mirrors out in open space, and now they're like, well, we're going to have to put a barrel around this mirror so it doesn't get whacked by micrometeorites.
Scott, you may have mentioned that, where will Roman be positioned? Like where will its point in space be? Well,
It'll be at the second Lagrange point, just the same place JWST is.
Okay.
Yeah. I think I forgot to mention that. I'm sorry. It's a very nice, quiet environment, I mean, aside from the micrometeorites, but it's a nice, quiet environment, and that makes a lot of things easier. So, expect more and more missions to be living out in L2. There's already quite a few of them out there now. Oh, by the way, if that confuses you, you shouldn't think of L2 as a single point, like they're all like crowded around each other and bumping into each other. L2 is actually a very large, semi-stable place in space that they can orbit around. So you can think of it as like a very large pasture for telescopes. So they're not bumping into each other. There's no risk of that.
Any other questions?
Good.
Thanks, Scott.
Thanks so much.
Thanks.
All right, I'm going to go back to writing my proposal. So thanks, everyone.
Thank you.
Thanks, Ray.
All right.
Like, have any, does anyone bring up?
It's larger than life feet.
Wow.
Oh, yeah. A little bit true, man. All right.
Everyone, reminder, next month, we have to confirm this, our meeting is going to be in the planetarium. Okay, and it will be an update on James Webb. So Mark Gagne from Westchester, who some of you were around in July, he kind of had a little program where they released some of the first images of James Webb. So we timed this purposely, so 6+ months into the mission, we'll get an update on new findings. But and he thought to do that, it would be best at planetarium. So stay tuned for the details.
Yeah, and I don't know if we can zoom from there.
Yeah, we may not be able to. So we'll have to tell people if you want to come, have to come.
Yeah, I don't know if there's a setup.
Yeah, I don't think there is.
Yeah. Okay.
Joe?
Hey, John, how you doing?